13.8 billion years after the Big Bang's genesis, you find yourself situated at the heart of all we can perceive. Beyond the most distant star, further than the furthest galaxy, an invisible barrier exists, impenetrable to telescopes, impervious to light. This marks the observable universe's edge. Yet imagine breaching this boundary, transcending it. Would you encounter an endless expanse of space, or would you uncover phenomena defying every known physical law? We embark on a journey into the realm of the impossible, venturing beyond the conceivable. Prepare yourselves. Our exploration begins. Envision yourself upon the shore of a boundless ocean, your vision limited only by the horizon. This mirrors our cosmic perspective. Light from the most distant celestial bodies has traversed the cosmos for over 13 billion years, hurtling at its ultimate speed. However, a pivotal twist alters our understanding. The universe itself expanded during this light's journey. Visualize a runner on an accelerating treadmill. The light represents the runner, and space-time, the ever-stretching treadmill beneath. Our most powerful telescopes reveal the cosmic microwave background radiation. This primordial light emanated when the universe achieved transparency, a mere 380,000 years post-Big Bang. Prior to this, the universe's heat and density prevented free light travel, akin to viewing through dense fog. Consider this cosmic background the universe's ultimate infancy portrait. But here lies the enigma. This ancient light wall forms a sphere around us, extending 46.5 billion light-years in all directions. We term this the observable universe, encompassing everything potentially visible. But the term observable conceals a daunting reality. The observable universe, however vast, is not the entirety of existence. It represents merely what we can currently perceive. The true extent of the universe, the actual universe, almost certainly surpasses this cosmic horizon. To what degree? That remains unknown. The analogy often employed by scientists is a cave with a single small opening. Through it, a limited portion of the outside world is visible. Mountains, oceans, or entire cities might exist unseen. Our cosmic horizon is analogous to this aperture, obscuring the universe beyond in perpetual darkness. Some researchers posit a universe beyond our horizon, closely resembling the one we observe. Countless galaxies, stars, and planets, traversing the infinite void. If this is accurate, then somewhere within this expanse, mirror images of our solar system could exist, duplicates of Earth, and even copies of you, this very moment reading these precise words. However, alternative, far more disconcerting hypotheses exist. These propose that beyond our cosmic sphere, the fundamental laws of physics might undergo a radical transformation. Space-time itself may curve, mirroring the surface of a balloon. The arrow of time might reverse its course. Matter could exhibit behaviors defying our current comprehension of reality. Perhaps the most unsettling prospect is the possibility of absolute nothingness beyond the horizon. Not merely emptiness or darkness, but a void so profound that even the concept of beyond becomes meaningless. We embark on a journey through theoretical landscapes, exploring cosmological possibilities that challenge our deepest intuitions. However, a foundational understanding of our perceived universe is paramount. We then encounter a startling revelation. The observable universe's edge recedes faster than any known velocity. This cosmic boundary hurtles outward at a speed approaching 3 times the speed of light, a feat seemingly impossible according to Einstein's theory of relativity, which posits that nothing can surpass the speed of light. Yet our observational horizon, relentlessly retreats into the cosmic darkness. The key lies in recognizing the nature of this expansion. It is not galaxies themselves traversing space at these phenomenal speeds. Rather, space itself is stretching, carrying galaxies passively, like flotsam on a cosmic river. Envision dots on an inflating balloon. The dots separate not due to their own movement, but because the balloon's surface expands. This expansion implies that, in this very moment, the observable universe is growing. New space becomes visible. Light, previously too distant, finally reaches us after a journey spanning billions of years. We witness the universe's unfolding in real time. Paradoxically, while the observable universe expands, we simultaneously lose sight of regions forever. Objects near the cosmic horizon are swept away so rapidly that their light will never reach us. They vanish beyond a point of no return, disappearing into an unexplored realm. Visualize a ship sailing away from a dock. Initially, the entire vessel is visible. Then the hull disappears below the horizon. Finally, even the tallest mast vanishes. Distant galaxies similarly fade into invisibility. This raises a crucial question. If the edge perpetually expands, why does a cosmic horizon exist? Why is our view not infinitely far-reaching in all directions? The answer resides in the universe's age. Since the Big Bang, light has had only 13.8 billion years to travel. Regardless of the expansion rate, light from beyond a certain distance simply hasn't had sufficient time to reach us. Scientists term this the particle horizon, representing the ultimate observational limit. Beyond this boundary lies the unobservable universe, potentially infinite, yet forever concealed from our observation. Recent measurements unveil a profoundly unsettling aspect of cosmic expansion. Its rate, contrary to gravitational expectations, is not decelerating, but accelerating. A mysterious force, termed dark energy by scientists, is driving this ever-increasing separation of space. This acceleration implies that galaxies currently at the limits of our observation will eventually vanish from view. Future civilizations, billions of years hence, will gaze upon a far emptier sky than ours. But what propels this relentless expansion, and what lies beyond the boundary it defines? If space extends infinitely beyond our cosmic horizon, then every conceivable eventuality must occur somewhere. This is the most intellectually challenging implication of an infinite universe. In a boundless realm, every possible configuration of matter and energy must exist somewhere within its vast expanse. Every conceivable historical trajectory, every conceivable version of you, every imaginable world. Mathematicians term this the principle of infinite probability. With limitless space and time, even the most improbable events become certainties. Consider an infinite sequence of coin tosses. Eventually, every possible sequence of heads and tails will appear, regardless of improbability. Visualize this cosmic lottery in action. Somewhere beyond our observational limit, a galaxy might exist, identical to our Milky Way. Within that galaxy, a solar system mirroring our own could harbor a planet just like Earth. On that planet, in a city resembling yours, someone bearing your exact likeness might be reading these very words at this precise moment. But the infinite universe does not conclude with mere duplicates. Worlds where history diverged would also exist. Earths where dinosaurs survived. Civilizations that achieved interstellar travel 1 million years ago. Planets where physical laws permit impossibilities like magic or time travel. The underlying mathematics is surprisingly robust. In an infinite universe composed of finite constituents, patterns must recur. Imagine ceaselessly typing random letters on a keyboard. Given sufficient time, every book ever written, every poem, every conceivable word combination would appear. The infinite universe functions similarly, but with atoms instead of letters. Some scientists extend this logic further, proposing that if the universe is truly infinite, not just copies of you exist, but an infinite number of them, countless versions living slightly different lives, making different choices, experiencing divergent outcomes. This concept should inspire awe, yet it also raises profoundly unsettling questions. If every conceivable version of your life exists, do your choices hold any genuine significance? If a version of you exists making every possible decision, what distinguishes your particular life as special or meaningful? The infinite universe hypothesis also gives rise to what philosophers call the Boltzmann brain paradox. In infinite space, random fluctuations of matter could spontaneously generate a conscious brain adrift in empty space. This brain would possess false memories of a complete life and world that never existed. Statistically, such randomly generated brains would vastly outnumber naturally evolved consciousnesses like ours. This leads to a troubling conclusion. If the universe is infinite, you are more likely to be a disembodied brain floating in space with fabricated memories than a real person residing on a real planet. The very act of reading this sentence could be merely an illusion born from random quantum fluctuations. Yet, perhaps the infinite universe is not the most extraordinary possibility confronting us as we peer beyond the cosmic horizon. We delve into a theory proposing our universe as a single bubble within a far vaster expanse. This astonishing conclusion stems from eternal inflation theory, a highly successful model in contemporary cosmology. The Big Bang, according to this concept, was not unique, but one among countless explosions occurring throughout a perpetually expanding superspace. Imagine blowing soap bubbles. Each is a self-contained world, yet all reside within the larger space of your yard. Cosmically, our universe is one such bubble, and the interbubble space is termed the bulk, a higher dimensional realm where conventional physics may not apply. The mechanism unfolds thus: quantum fluctuations within the bulk trigger regions of space to inflate at phenomenal speeds. Each inflation event generates a new universe bubble, complete with its own Big Bang, space, time, and potentially unique physical laws. Concurrently, the bulk expands, accommodating the formation of more universe bubbles. Therefore, beyond our cosmic horizon, new universes are currently being born, each initiating with its own Big Bang and expanding into its own private space. Some of these universes might resemble ours, possessing familiar particles and forces, while others could be radically different, exhibiting utterly alien physics beyond our comprehension. Consider each universe bubble possessing its own set of reality instructions. In our universe, electrons have specific charge and mass. Gravity adheres to Einstein's equations, and light travels at a constant speed. However, in other bubbles, electrons might be 10 times heavier, gravity could be repulsive instead of attractive, or time might flow in multiple directions simultaneously. The boundaries between these universe bubbles constitute some of the most extraordinary regions imaginable. When two expanding bubbles collide, a collision zone forms where the physical laws of both universes clash and intermingle. These cosmic crash sites might produce phenomena so bizarre as to defy description. Some scientists suggest detecting evidence of other universe bubbles by searching for subtle patterns in our cosmic microwave background radiation. A past collision with another bubble would leave an imprint in the ancient light permeating our space. However, the truly unsettling aspect is this. If the bubble multiverse is real, our observable universe represents an infinitesimally small fraction of existence. Not only are we confined to a single bubble among countless others, but we can perceive only a minuscule portion of our own bubble. It is akin to a microbe on a soap bubble, seeing only a small patch of its surface, oblivious to the immense foam surrounding it. The bubble multiverse also raises profound questions about the nature of existence itself. If infinite universes exist with every conceivable set of physical laws, what makes our universe special? However, even the bubble multiverse might be too simplistic to fully capture reality's strangeness. Each decision you've ever made has, according to the many worlds interpretation of quantum mechanics, fractured the universe. This extraordinary theory posits that reality branches into parallel universes with every quantum event, occurrences happening constantly, everywhere, at the subatomic level, across the cosmos. As you read this, countless quantum particles within your brain are making probabilistic choices, determining their paths, energy levels, and spin directions. The many worlds theory asserts that each of these minuscule decisions generates a new branch of reality. In one branch, the particle veers left, in another, right. Both realities are equally valid, and both versions of you continue to exist in parallel. Imagine reality as an immense tree with infinite branches. The trunk symbolizes the universe's origin, each quantum event adding a new fork. Over 13.8 billion years, this cosmic tree has become incredibly complex, encompassing every conceivable historical unfolding. This implies that within the quantum multiverse, branches exist where you made different choices, alternate realities where you pursued a different career, married someone else, or never existed at all. Universes exist where dinosaurs achieved intelligence, where humanity never left Africa, or where Earth never formed. The underlying mathematics is surprisingly elegant. In quantum mechanics, particles exist in superposition, meaning they can occupy multiple states simultaneously until observed. Conventional quantum theory states observation collapses the particle into a single state. However, many worlds theory suggests observation splits reality, with every potential particle state existing in its own parallel universe. Consider a quantum coin flip. In our daily experience, the coin shows either heads or tails, but within the many worlds framework, reality bifurcates. One branch showing heads, the other tails. Both outcomes occur, but in separate parallel universes. The truly astounding aspect is the frequency of these splits. Every quantum interaction in every atom, every star, every galaxy generates new reality branches. The number of parallel universes grows exponentially with each passing moment, resulting in a vast multiverse containing more timelines than atoms in our observable universe. Some many worlds interpretations posit these parallel universes exist beyond our cosmic horizon, arranged like infinite sheets of paper within higher dimensional space. Others propose they coexist within our universe, vibrating at different quantum frequencies, much like radio stations on different channels. However, the unsettling aspect of quantum many worlds is this. If every possible reality exists within the multiverse, then so does every possible form of suffering. For every universe where you live a fulfilling life, countless others might exist where you experience tragedy, pain, or loss. The quantum multiverse compels us to confront uncomfortable questions about identity and meaning in a reality where every possible version of everything exists simultaneously. Even this astonishing concept may not fully encompass the vastness beyond our cosmic boundary. Reality itself could be purely mathematical, with physical matter an illusion. This radical notion, put forth by cosmologist Max Tegmark, suggests our universe isn't composed of particles, fields, or energy, but of mathematical relationships that somehow perceive themselves as physical reality. Should this theory prove accurate, then beyond our cosmic horizon lies not more space, but more mathematics. Consider the contrast between a video game and its underlying computer code. Within the game, characters encounter trees, buildings, and landscapes that feel entirely real. However, outside the game, only code, numbers, equations, and logical operations exist. Tegmark posits that we resemble these video game characters, experiencing mathematical code as physical reality. This mathematical universe hypothesis transcends the simple observation that mathematics accurately describes the physical world. It asserts that mathematics does not merely describe reality, mathematics is reality. There is no distinction between a mathematical structure and the physical universe it represents. Consider how this might function. Each electron in your body possesses properties like charge, mass, and spin. But what if these properties aren't inherent attributes the electron has, but rather mathematical relationships the electron is? What if an electron is merely a specific informational pattern, a unique solution to mathematical equations governing quantum fields? If the mathematical universe theory holds true, then beyond our observable boundary lies every conceivable mathematical structure. Universes based on different geometries, varying numbers of dimensions, and entirely different logical systems would exist. There would be universes where space possesses 17 dimensions, where time branches into multiple streams, where causality operates in reverse. Some of these mathematical universes would be so alien that conscious beings like ourselves could never exist within them. Others might support forms of consciousness beyond our comprehension. Imagine mathematical structures where awareness emerges from pure number theory, where thoughts are geometric transformations, and where memories are topological features of abstract space. The implications are even more profound. If consciousness itself is a mathematical pattern, then every possible form of awareness must exist somewhere within the mathematical multiverse. Minds would exist that experience reality as music, others that think in colors outside our spectrum, and perhaps some that perceive all of mathematics simultaneously. However, this theory also presents a profound enigma concerning existence itself. If every possible mathematical structure exists, why do we find ourselves in this specific one? Why do we experience a universe with 3 spatial dimensions, 1 time dimension, and the precise physical constants that permit star and planet formation? Some researchers suggest that most mathematical structures are either too simple or too chaotic to support complex consciousness. We exist in this particular universe not because it is special, but because it is among the few mathematical structures complex enough to contain beings capable of posing these questions. The mathematical universe compels us to reconsider everything we believe we know about the nature of existence, reality, and our place within it. Perhaps the most unsettling cosmological possibility is that nothing exists beyond our cosmic horizon. What if our universe is all there is, isolated in an infinite void of absolute nothingness? This possibility deeply troubles cosmologists studying the shape and size of space-time itself. While most scientists posit a universe extending far beyond our observational capabilities, a contrasting scenario fundamentally alters our perspective. Our cosmos might be a finite island of existence, entirely surrounded by pure emptiness. Imagine a single soap bubble within a vast, empty warehouse. The bubble encompasses all the air, all the matter, and all the energy in existence. Beyond the bubble is not merely different air or matter, but absolute vacuum. Not the vacuum of space, which still contains quantum fields and virtual particles, but true nothingness. No space, no time, no possibility of existence whatsoever. In this scenario, our universe's edge would represent the most terrifying boundary imaginable. It would be inaccessible, uncrossable, because there would be no there to go to. The concept of beyond becomes meaningless, akin to asking what lies north of the North Pole, or what preceded the beginning of time. The mathematics of general relativity accommodates such finite universes. Space could curve back upon itself, like a sphere's surface, resulting in a cosmos of definite size and boundary. Fast enough, far enough travel in a single direction would eventually return you to your origin point, similar to a ship sailing east around Earth, returning from the west. However, unlike a sphere embedded in three-dimensional space, our curved universe would lack such embedding. No higher dimensional space would exist for it to curve through. The universe would be intrinsically finite, a complete and self-contained reality with edges touching nothing. Some models suggest our universe's shape resembles a donut, a pretzel, or even more exotic geometric forms. Each shape would generate unique patterns in the cosmic microwave background radiation, offering potential avenues to test for spatial boundaries. The psychological ramifications of inhabiting a finite universe would be profound. Instead of insignificant specks in an infinite cosmos, we would be inhabitants of the sole island of existence, past, present, and future. Every atom, every star, every galaxy would possess immeasurable value, as nothing else would exist anywhere. This finite universe scenario also raises profound questions about its origin. If nothing exists outside our cosmic bubble, what brought it into being? What dictates its size and shape? Why this particular finite universe, rather than a different one or none at all? The prospect of cosmic loneliness, of being the only pocket of existence in an infinite void, might prove more unsettling than any multiverse theory we have contemplated. A possibility more perplexing than a universe of finite extent exists, that space-time itself might be contorted, creating impossible connections. Gazing towards the observable universe's edge, we might, astonishingly, be observing ourselves. This mind-bending concept stems from the peculiar geometry of curved space, where the universe could resemble a hall of mirrors, generating infinite reflections within a finite volume. If this is so, then the most distant galaxies we detect might actually be nearby galaxies, viewed from impossible angles, their light having circumnavigated a curved cosmos. Envision residing within a house, entirely lined with perfect mirrors. You would perceive countless duplicates of yourself and your belongings extending infinitely. These, however, would not represent separate rooms or individuals, but rather reflections of the same single room, the same single you. A cosmic mirror universe functions similarly, with space itself acting as the reflective surface. In this scenario, the universe possesses a finite size, yet lacks edges. Space curves back upon itself in intricate ways, a non-trivial topology, as mathematicians term it. Consider an ant traversing a donut's surface. It can journey endlessly without encountering a boundary, yet will inevitably revisit previously traversed locations, as the surface's area is finite. Should our universe exhibit this twisted geometry, then observing opposite directions in the sky might reveal the same spatial regions from differing perspectives. The cosmic microwave background radiation observed in the north could be identical to that seen in the south, viewed from a different angle after its light has completed a circuit around the curved universe. Scientists are actively searching for evidence of this cosmic mirror effect, seeking matching patterns in the cosmic microwave background's temperature fluctuations across disparate sky regions. The discovery of such matching patterns would confirm space-time's self-curvature and our residence within a hall of cosmic mirrors. This discovery would fundamentally alter our comprehension of the universe's size and structure. Instead of spanning 13.8 billion light-years, the actual universe might be far smaller, perhaps only a few billion light-years in circumference. Every distant galaxy, every far-off quasar, every remote region we observe, would in reality be relatively proximate, viewed through the distorted geometry of curved space-time. This, however, presents a troubling conundrum regarding observation and reality. If we can perceive the same galaxy from multiple directions, as light traverses different paths around the curved universe, which view accurately represents the galaxy's true state? Are we observing it in its current state, or as it existed at various past times, as light takes shorter or longer routes to reach us? The cosmic mirror universe also raises questions of uniqueness and identity. If space curves back upon itself, then every point in the universe could be interconnected with every other point via multiple paths. The distinction between here and there, between near and far, would become fundamentally meaningless. Yet, perhaps the most profound enigma resides not in the geometry of space, but in the nature of nothingness itself. What does it signify for nothing to exist? And how can non-existence be something that resides beyond our universe? This query strikes at the core of philosophy's most profound enigmas. When scientists discuss what lies beyond the observable universe, they frequently employ the word nothing, as if it denotes a location or an entity. But genuine nothingness cannot be a place, for places necessitate space. It cannot be a thing, because things necessitate existence. True nothingness is the absence of absence itself. Consider the distinction between an empty box and no box whatsoever. The empty box still encompasses space, still possesses dimensions, still exists as a container. But true nothingness would be the absence of even the box itself. No container, no space for containment, no possibility of containment. It is not darkness, because darkness implies the absence of light in a place where light could exist. It is not silence, because silence implies the absence of sound in a place where sound could occur. Philosophers have grappled with this concept for millennia. The ancient Greeks pondered whether nothing could be something, and whether something could originate from nothing. They recognized that even contemplating nothing renders it something, because it becomes an object of thought. The very act of imagining nothingness grants it a form of existence within our minds. Modern physics has further complicated this picture. Quantum mechanics reveals that what we term empty space is actually replete with virtual particles appearing and disappearing, zero-point energy fluctuations, and quantum fields pervading every spatial point. The vacuum of space is not nothing. It is a highly active something that simply happens to be invisible. Yet beyond the edge of our universe, we might encounter a different kind of nothing. Not the quantum vacuum of empty space, but the absence of space itself. No dimensions, no fields, no possibility of anything existing or occurring. This is the type of nothing that renders the question, what is beyond the universe, potentially meaningless, akin to asking what color the number 7 is, or whether silence possesses a taste. Some philosophers contend that true nothingness is impossible, because existence is reality's fundamental nature. In this perspective, something has always existed and always will exist. the question becomes not whether anything exists beyond our universe, but what kind of something it might be. Others posit that nothingness is not only possible, but inevitable, suggesting that existence is the unusual state, and that most of reality comprises the absence of reality. Within this framework, our universe is a rare bubble of something adrift in an infinite ocean of nothing. The debate touches upon existence's deepest questions. Why is there something rather than nothing? What makes existence possible? Is the absence of everything a coherent concept? Does the universe possess an edge, a boundary beyond which nothing exists? Or does it crumble under its own inherent contradictions? These inquiries transcend mere philosophical musings, for their resolution might dictate the ultimate destiny of all that we hold dear. But perhaps the most crucial question isn't what lies beyond the universe, but rather what the very pursuit of answers unveils, about the essence of human inquisitiveness. Each cosmic enigma solved reveals a far vaster expanse of the unknown. This constitutes the fundamental paradox of exploring the cosmos. The deeper our understanding of space, time, and reality becomes, the more unforeseen questions arise. Every breakthrough in physics ushers in new mysteries, eclipsing the problems we believed we had solved. Consider the evolution of our comprehension over the last 100 years. When Albert Einstein formulated general relativity, scientists envisioned a universe static and eternal. Then Edwin Hubble's discovery of the universe's expansion compelled us to acknowledge a cosmic genesis. Subsequently, the identification of dark matter and dark energy revealed that ordinary matter constitutes only 5% of existence. Now, we grapple with the possibility that our observable universe might be a minuscule fragment of something infinitely grander. Each discovery has pushed the frontiers of knowledge further, akin to chasing a sunset that recedes as swiftly as we approach it. Galaxies were once considered the universe's largest structures, until we discovered galaxy clusters. Galaxy clusters held that title until we found superclusters and cosmic filaments. Our universe was deemed all-encompassing until theories proposing multiverses containing countless universes emerged. This pattern exposes a profound connection between human consciousness and cosmic reality. We are biological entities, evolved on a small planet, with brains designed to comprehend objects of moderate size, moving at moderate speeds within our immediate surroundings. Yet these same brains can contemplate infinity, grasp quantum mechanics, and envision realities beyond any possible observation. Reflect on the mathematical tools employed to probe existence's edge. Differential equations describing space-time curvature, quantum field theories predicting the behavior of virtual particles, statistical mechanics explaining the arrow of time. These are not concepts for which natural selection prepared us, yet we understand them, at least partially. This suggests something extraordinary about the nature of intelligence itself. Consciousness might not be a mere biological accident, but a fundamental property of reality, enabling the universe to comprehend itself. We are not simply observers of cosmic enigmas. We are the universe becoming cognizant of its own being. Yet, our duty as cosmic investigators carries profound implications. Each inquiry we undertake regarding the expanse beyond the observable universe concurrently probes the nature of our existence as conscious, rational entities within a cosmos potentially far more enigmatic than we can presently fathom. Humanity's most ambitious endeavor has consistently been the pursuit of knowledge. This quest has propelled us to construct telescopes capable of penetrating the depths of space, far exceeding the limits of human vision. to formulate mathematical frameworks describing realities beyond the grasp of complete mental comprehension, and to pose questions that might remain unanswered. As we find ourselves at the boundary of the observable universe, gazing into the uncharted territories of the cosmos, we simultaneously examine our inner selves. The enigmas that reside beyond our cosmic horizon serve as mirrors, reflecting the profound mystery of consciousness itself. Our voyage to comprehend what lies beyond the limits of all that is known is merely in its nascent stages. What if everything beyond our cosmic horizon is simply more computer code, running on an alien supercomputer? This is not science fiction speculation, but a serious scientific hypothesis proposed by philosopher Nick Bostrom and embraced by physicists such as Neil deGrasse Tyson. The simulation theory suggests that our entire universe, including everything we believe lies beyond it, might be an artificial reality created by some advanced civilization. Consider how rapidly our own computer simulations have evolved. 50 years ago, the most advanced video games were simple dots moving across a screen. Today we create virtual worlds so realistic that players can spend entire lifetimes exploring digital landscapes that feel completely, undeniably real. If this trend continues, future civilizations might develop computers powerful enough to simulate entire universes, complete with billions of conscious beings who never suspect they are living inside a program. The mathematics underlying this idea are surprisingly compelling. If advanced civilizations can create realistic universe simulations, they would likely run many of them for research, entertainment, or educational purposes. This implies countless simulated universes for every real one. Statistically speaking, any conscious being is far more likely to exist inside a simulation than in base reality. The implications extend far beyond our cosmic horizon. If we are simulated beings, then the edge of our observable universe might simply be the boundary of the computer program running our reality. Beyond that edge might not be more space or parallel universes, but the alien equivalent of computer memory, processing cores, and cooling systems. Evidence for the simulation hypothesis might already exist within the fundamental structure of reality. Quantum mechanics behaves remarkably like the optimization tricks programmers use to conserve computing power. Particles exist in undefined states until observed. Just like video game landscapes that only render in detail when a player looks at them, the universe has a maximum speed limit, much like computers have maximum processing speeds. Space and time appear to be quantized at the smallest scales, just as digital information is broken into discrete bits. Some researchers propose that we might detect glitches in our simulated reality by searching for inconsistencies in physical laws or mathematical constants. Others suggest that the cosmic microwave background radiation might contain hidden messages from our programmers, like digital signatures embedded in the code. However, the simulation hypothesis creates a troubling recursive problem. If we are simulated beings who develop our own universe simulations, then the beings in our simulations might also develop simulations, creating an infinite nested hierarchy of artificial realities. Each level would believe their simulated universe represents the full extent of existence, never knowing they are characters in someone else's digital world. The question becomes, how many levels deep might this simulation stack extend? Are we first-level simulations run by biological beings? Or are we simulations of simulations of simulations nested so deeply that the original creators are lost in the recursive layers? If the simulation hypothesis is true, then the search for what lies beyond our universe becomes a search for the hardware running our reality. The most unsettling cosmological possibility, perhaps, is that space itself might be an illusion, masking a far more fundamental reality. What we perceive as three-dimensional space could in fact be encoded on a two-dimensional surface at the universe's edge. This revolutionary concept, the holographic principle, proposes that all information defining our three-dimensional universe is stored on a distant two-dimensional boundary, a cosmic hard drive, as it were, projecting reality into our local space-time. If accurate, then beyond our observable universe lies not more space, but the surface where our entire existence is inscribed in quantum code. Consider a hologram on a credit card. The image appears three-dimensional, yet all information creating this illusion is encoded on the card's flat surface. The holographic principle suggests our universe functions similarly. Each particle, force, and event within our three-dimensional space is information encoded on a two-dimensional boundary, inaccessible and unobservable to us. This idea's mathematical underpinnings emerged from black hole research. Physicist Jacob Bekenstein discovered that a black hole's information capacity is proportional to its surface area, not its volume. This was astonishing, as three-dimensional objects should store information throughout their volume, not solely on their surface. However, black holes behave as fundamentally two-dimensional entities, appearing three-dimensional only from our perspective. Stephen Hawking expanded this understanding by discovering that black holes emit radiation. Information entering a black hole must be preserved within the emitted radiation, albeit in a scrambled, unreconstructible form. This indicates the black hole's surface acts as a holographic screen, processing and storing information about everything crossing the event horizon. Physicist Juan Maldacena subsequently proved this holographic principle applies to entire universes, not just black holes. His mathematical framework equates our three-dimensional space with gravity to a two-dimensional surface devoid of gravity. These are not merely similar or analogous, they are identical, viewed from different perspectives, like observing the same object from varying angles. If the holographic principle holds true, our observable universe's edge might be this cosmic holographic screen's location. Everything we experience as three-dimensional reality would then be a projection from information encoded on that distant boundary. Space, matter, energy, and even time itself would be emergent phenomena stemming from deeper two-dimensional patterns. This presents a profound enigma concerning distance and separation. If all information describing you is encoded on a faraway surface, in what sense do you exist here rather than there? The distinction between inside and outside, between local and remote, becomes fundamentally meaningless. The holographic principle also suggests reality contains far less information than it seems. Instead of each point in three-dimensional space requiring its own description, all this information is compressible onto a two-dimensional surface without detail loss. But if space is merely a holographic illusion, what does this reveal about other mysteries encountered when we transcend conventional reality? The interior of every black hole may contain an entire universe, potentially exceeding our own in size. This astonishing possibility arises from the mathematical descriptions of extreme gravity and the unusual behavior of space and time near the event horizon. When matter collapses to form a black hole, the intense gravitational field generates regions where the familiar laws of physics completely fail. Within this breakdown, entirely new universes might originate. Consider the fate of a massive star exhausting its fuel and collapsing under its own gravity. The core shrinks with such speed that it generates a gravitational field capable of trapping light itself. From an external perspective, we observe an event horizon, a boundary beyond which nothing can escape. However, internally, something far more extraordinary may be occurring. Some theories posit that the collapsing matter does not simply form a singularity, a point of infinite density. Instead, these extreme conditions might trigger a kind of reverse Big Bang, producing an expanding universe on the opposite side of the event horizon. This new universe would be utterly isolated from our own, possessing its own space, its own time, and its own physical laws. Envision this as a cosmic birthing process. Each time a black hole forms in our universe, it potentially births a baby universe that expands within the event horizon. These nascent universes would remain imperceptible to us, as no information can traverse the event horizon to reveal what transpires within. From our viewpoint, the black hole appears as a terminus, where matter and energy vanish eternally. Yet, from within, it could represent the genesis of an entirely new cosmos. Mathematical models suggest that these black hole universes could be immense, perhaps encompassing billions of galaxies and persisting for trillions of years. The event horizon, seemingly minuscule from our perspective, might enclose a space larger than our entire observable universe. Time dilation effects near the black hole imply that billions of years could elapse internally, while only seconds pass in our external frame of reference. This establishes a nested hierarchy of universes within universes. If black holes in our universe generate baby universes, then black holes within those baby universes might create their own progeny, resulting in an infinite family tree of cosmic generations. Each universe would produce countless offspring, and each of those offspring would generate countless more. The implications for what exists beyond our cosmic horizon are breathtaking. Instead of questioning what lies outside our universe, we might need to inquire about our generation within this cosmic family tree. Are we a first-generation universe formed naturally, or do we reside inside a black hole created by a parent universe we can never observe? Some researchers suggest that our own Big Bang might have been the interior of a black hole formed within a higher-level universe. The rapid expansion we observe could be the inherent behavior of space and time within an event horizon, making our observable cosmos merely the interior of one black hole among countless others. The true nature of what lies beyond our universe may depend on something even more fundamental than space and gravity. Time itself might flow backward beyond the edge of our universe, creating regions where effect precedes cause and the future dictates the past. This possibility arises from the deepest mysteries of thermodynamics and the curious fact that the laws of physics are almost entirely time-symmetric. Most fundamental equations function equally well whether time flows forward or backward. Yet we experience a universe where time possesses a clear direction, from past to future, from order to disorder, from cause to effect. The arrow of time we perceive originates from the second law of thermodynamics, which dictates that entropy, or disorder, invariably increases in isolated systems. Consider a drop of food coloring dispersing in a glass of water. The coloring always spreads from concentrated to dispersed, never the opposite. This establishes our sense of temporal direction, our feeling that some moments precede others. But this raises a profound question. Why did our universe commence in a state of low entropy? The Big Bang began with matter and energy arranged in an extraordinarily organized configuration, which has been growing more disordered ever since. This initial state was so improbable that some cosmologists liken it to observing 1 billion coin flips, all landing heads up by pure chance. Beyond our cosmic horizon, the arrow of time might point in the reverse direction. In these regions, entropy would decrease instead of increase, broken objects would spontaneously self-repair. Scattered particles would coalesce into organized structures. Dead stars would revive by absorbing their own radiation. Imagine traversing a cosmic boundary where the arrow of time reverses. On one side, you would observe normal physics with clear cause and effect relationships. But crossing the boundary, you would enter a realm where effects precede causes, where events unfold from future to past, where memory operates in reverse, and prediction becomes a record of what has already occurred. The mathematics of such time-reversed regions are compatible with general relativity and quantum mechanics. These zones would appear perfectly normal to any inhabitants residing within them, because their consciousness and memory would also function in reverse temporal order. They would experience their version of cause and effect as natural and logical, just as we experience ours. Some cosmological models posit that our universe exists at the boundary between two vast regions with opposing arrows of time. Our Big Bang might represent the point where two time streams intersect, creating a zone where entropy can decrease in both temporal directions simultaneously. This would render our observable universe a kind of temporal estuary where different flows of time converge and blend. If regions with reversed time exist beyond our horizon, they would be fundamentally imperceptible to us. Light traveling from those regions would appear to us as if it were traveling into the past, creating logical paradoxes that might prevent any information from traversing the temporal boundary. The arrow of time may not be a universal feature of reality, but a local property of our specific region of space. Yet, perhaps time itself is merely another illusion concealing an even deeper truth about the nature of existence. In the far, far future, our universe will expand into a cold, dark emptiness where even atoms decay into nothing. Yet, beyond the limits of our observation, this cosmic demise might be the very seed of endless renewal. This ultimate fate, predicted by the laws of thermodynamics, is known as heat death, the final state where entropy reaches its maximum and all energy distributes evenly throughout space. Stars will exhaust their fuel, black holes will evaporate, and even protons will decay into elementary particles. The universe will become a vast, empty expanse, populated only by photons and neutrinos, drifting ever farther apart. Imagine heat death as a cosmic cup of hot coffee cooling to room temperature. Initially, temperature differences drive energy flow and enable work. But eventually, thermal equilibrium arrives, and further work becomes impossible. The universe then becomes a uniform sea of low-energy particles, devoid of structure, information, and the potential for change. However, this apocalyptic vision might only apply to our local region of space-time. Beyond our cosmic horizon, vastly different thermal environments could exist. Some areas may be in earlier stages of cosmic evolution, with young stars forming and galaxies growing. Others might be closer to their own heat death, while others still may operate under entirely different thermodynamic principles. The process of heat death is expected to unfold over an almost unimaginable timescale. Current estimations suggest that the last stars will burn out in about 100 trillion years. Black holes will evaporate far more slowly via Hawking radiation. The most massive black holes might persist for 10 to the 100th power years before ultimately disintegrating into elementary particles. Even after heat death, however, quantum mechanics suggests the universe might not remain eternally lifeless. Over an infinite expanse of time, random quantum fluctuations could spontaneously generate new structures, new complexities, even new life. Given sufficient time, these fluctuations might, through pure chance, reconstruct entire universes. Some cosmologists propose that heat death represents not an ending, but a transition. The maximum entropy state might prove unstable over cosmic timescales, eventually collapsing or transforming into new phases of cosmic evolution. What seems like the end of everything may actually be the prelude to a new beginning. Beyond our observable boundary, some regions might have already experienced heat death and rebirth numerous times. They could be in their second, third, or millionth cycle of cosmic evolution, having perhaps learned to transcend thermodynamic limitations through mechanisms beyond our current comprehension. This heat death scenario also raises profound questions about the purpose and meaning of existence within a finite universe. If everything we build, everything we create, everything we discover will ultimately be erased by cosmic expansion and entropy, what then gives our lives meaning in the face of such ultimate futility? Perhaps the answer resides not in conquering heat death, but in recognizing that our fleeting moment of cosmic organization represents something precious and unprecedented within the vast expanse of space and time. But what if the boundaries separating death and rebirth, ending and beginning, are not as clearly defined as they initially appear? At present, there exists a minuscule yet genuine possibility that you could spontaneously quantum tunnel through the very edge of space itself and materialize in a completely different universe. This extraordinary prospect originates from quantum mechanics, a field where particles occasionally traverse barriers deemed insurmountable. According to classical physics, mathematical calculations demonstrate that even large objects, including human beings, possess a non-zero probability of tunneling through any barrier, regardless of its apparent thickness or impenetrability. Imagine throwing a ball at a brick wall. In classical physics, the ball invariably rebounds. However, in quantum mechanics, a minuscule chance always remains that the ball will pass directly through the wall, as if it were non-existent. This probability diminishes drastically for larger objects such as balls, but it never reaches precisely zero. This same principle might govern the boundaries of space itself. If our universe possesses edges or boundaries separating it from other realms of reality, then quantum tunneling could enable matter and energy to traverse these boundaries spontaneously. You could theoretically tunnel from within our cosmic horizon to whatever lies beyond. The probability of such large-scale tunneling is exceptionally low. The likelihood of a human spontaneously tunneling through the cosmic boundary would be approximately 1 in 10 to the power of 10 to the power of 50. This number is so astronomically large as to be beyond human comprehension. One would need to wait far longer than the age of 13.8 billion years for such an event to possess even a remote possibility of occurring. But in an infinite multiverse encompassing infinite time, even impossibly improbable events become inevitable. Somewhere in the boundless expanse of space and time, copies of you are perpetually tunneling between different regions of reality, exploring universes with varying physical laws, distinct histories, and diverse possibilities. The process would be instantaneous and imperceptible from our perspective. One moment you would be here, reading these words in our familiar universe. The next moment, a quantum-tunneled version of you would exist in a completely alien reality, potentially retaining all your memories, yet finding yourself in a world where the laws of physics operate differently. Some interpretations of quantum mechanics suggest that this tunneling occurs continuously at the subatomic level. Every quantum particle within your body might be constantly tunneling between different branches of the multiverse, with most tunneling events being so minuscule as to go unnoticed. But occasionally, larger tunneling events might transpire, shifting entire molecules or even larger structures between different realities. the implications extend beyond personal inter-universal transportation. Quantum tunneling might permit information leakage between distinct regions of the cosmic multiverse. The random quantum fluctuations we observe in seemingly empty space might actually be signals from neighboring universes, faint whispers of alien realities seeping through the quantum foam. If quantum tunneling can indeed traverse cosmic boundaries, then the edge of our universe might not be a permanent barrier, but rather a permeable membrane. Matter, energy, and information might constantly flow between our reality and whatever lies beyond, creating a cosmic ecosystem where different universes exchange resources and mutually influence each other's evolution. The most extraordinary possibility, perhaps, is that our universe itself originated from cosmic tunneling. What if our Big Bang wasn't the absolute beginning, but merely the most recent explosion in an unending sequence of cosmic death and rebirth? This is the core concept of cyclic cosmology. The universe expands, ages, perishes, and then rebounds into a new Big Bang, eternally repeating. If true, beyond our cosmic horizon might reside remnants of past cosmic cycles, the seeds of future universes, and the mechanisms driving this endless cosmic reincarnation. Envision the universe as a colossal cosmic heart, beating once every 1 trillion years. Each beat involves space expanding from a minuscule point, growing immensely, then contracting back to a point before exploding outward anew. We currently inhabit the expansion phase of one such cosmic heartbeat. However, countless previous beats preceded us, and countless more will follow. The mathematical framework of this cyclic model resolves several enigmas that challenge the standard Big Bang theory. Rather than questioning the Big Bang's cause, or its antecedent, cyclic cosmology simply posits a preceding universe that collapsed and rebounded. The remarkable fine-tuning needed for our universe to sustain stars, planets, and life becomes less perplexing if the cosmos has had infinite opportunities to experiment with various combinations of physical constants. In the cyclic model, the edge of our observable universe might hold traces of prior cosmic cycles. Ancient gravitational waves from earlier Big Bangs might still be traversing space, conveying information about universes existing trillions of years ago. The subtle patterns within the cosmic microwave background reveal the structure of the universe that existed before ours. Each cycle would subtly differ from its predecessor. Quantum fluctuations during the collapse and rebound phases would guarantee that no two cosmic cycles are precisely identical. Some cycles might produce universes resembling ours, replete with stars and galaxies. Others might create cosmos dominated by black holes or filled with exotic matter beyond our comprehension. The transition between cycles would constitute the most extraordinary event in all of physics. As space contracts during the collapse phase, galaxies would converge, stars would merge, and eventually all matter and energy would be compressed into a region smaller than an atomic nucleus. At this point of maximum compression, quantum effects would intensify, potentially causing space and time themselves to break down and reform under different laws. Consider this cosmic recycling process the ultimate form of sustainability. Nothing is truly lost or wasted. Every atom ever to exist, every thought ever conceived, every star ever to shine, gets compressed, processed, and reborn in the subsequent cosmic cycle. Death transforms into birth. An ending becomes a beginning. The universe achieves a form of immortality through perpetual transformation. Yet, if we reside in a cyclic universe, profound questions about identity and meaning arise. Are we truly unique individuals, or are we variations on themes played out countless times in prior cosmic cycles? The answer might depend on forces operating in dimensions beyond our perception. Unseen, untouchable, and right alongside us, entire universes may exist within dimensions beyond our comprehension. This isn't science fiction, it's a serious possibility arising from string theory and higher dimensional physics. Mathematical models suggest our familiar three-dimensional space is merely a thin slice of a far grander reality, encompassing 6, 7, or even 11 spatial dimensions. Each could potentially harbor its own unique existence. Consider a two-dimensional being inhabiting a piece of paper. Its perception of our three-dimensional world would be limited. It might observe our fingers as enigmatic circles, appearing and vanishing as we move our hands above and below its paper universe. Similarly, higher dimensional beings might surround us, their presence detectable only as peculiar anomalies and subtle influences within our three-dimensional space. These extra dimensions could be incredibly compact, imperceptible at typical scales, like a garden hose appearing one-dimensional from a distance, yet revealing its circular cross-section upon closer inspection. These tightly curled dimensions could be smaller than atoms, yet potentially define the fundamental characteristics of particles and forces within our observable universe. String theory necessitates these extra dimensions for its mathematical consistency. In this framework, what we perceive as particles are actually minuscule, vibrating strings, traversing all 11 dimensions. Their vibrational patterns within these extra dimensions determine whether a string manifests as an electron, a photon, or any other particle type. However, some higher dimensional theories propose the existence of entire universes within parallel dimensions, expansive rather than minuscule. These universe-sized extra dimensions would be entirely separate from ours, possessing their own matter, energy, and potentially their own life forms. We would be imperceptible to them, and they to us, as we're confined to distinct dimensional slices of the same higher dimensional space. The boundary of our universe might not be a three-dimensional edge, but a limitation of our reach into these higher dimensions. Beyond our cosmic horizon might lie not more three-dimensional space, but access to these concealed dimensions, where wholly different realities operate according to geometric principles beyond our visualization capabilities. Gravity might be the only force capable of traversing dimensions, potentially explaining its relative weakness compared to electromagnetism and the nuclear forces. Some gravitons might escape our three-dimensional space into these extra dimensions, carrying energy away to universes we can never observe or reach. Scientists seek evidence of extra dimensions by searching for minute deviations in gravitational behavior at extremely small scales. If gravity exhibits unexpected strength at distances smaller than 1 millimeter, it might suggest gravitons are confined to fewer dimensions at short ranges. The discovery of large extra dimensions would revolutionize our understanding of the cosmos beyond the observable universe. Instead of questioning what exists outside our space, we would need to consider what lies outside our dimensional slice of a vastly larger, higher dimensional reality. Perhaps the most perplexing notion is that consciousness itself plays a fundamental role in defining which dimensions become real. The simple act of observing the universe may be the very act of creating the reality that extends beyond our cosmic horizon. This mind-bending concept arises from quantum mechanics, where the act of measurement seems to transform possibilities into actualities. In the quantum realm, particles exist in superposition, simultaneously occupying multiple states until the moment they are observed. Then, the wave function collapses, and reality selects one specific outcome from among all the possibilities. But what if this observer effect operates not just on individual particles, but on the very fabric of space-time itself? What if the universe beyond our horizon exists in quantum superposition, containing every possible configuration simultaneously until we observe it, forcing it to select a specific reality? Imagine reality as an infinite garden of forking paths, where every possible universe exists in quantum superposition until conscious observation collapses the wave function and selects a single path. The edge of our observable universe might represent the boundary between the collapsed, definite reality we have observed and the uncollapsed probabilistic reality existing in superposition beyond our perception. This interpretation suggests that the universe has been growing and solidifying into definite form as consciousness has evolved and expanded its reach. Early in cosmic history, when observers were absent, most of reality may have existed in pure superposition. As stars formed and eventually birthed planets with conscious life, those observers began collapsing larger and larger regions of space into definite states. The implications are astounding. Each time astronomers point a telescope toward a previously unobserved region of space, they may be literally creating that part of the universe by forcing it to choose specific properties. The galaxies they discover may not have possessed definite positions, masses, or ages until the moment of observation collapsed their quantum wave functions. Quantum mechanics suggests that consciousness is not merely observing reality, but actively participating in its creation. The universe might be engaged in an ongoing dialogue with conscious observers, where each act of observation reshapes the possibilities for what can exist beyond the current limits of our knowledge. However, this raises profound questions about the relationship between mind and cosmos. If observation creates reality, then what existed before conscious beings evolved? Did the universe exist in pure potential until the first conscious observer collapsed its wave function? Or does consciousness itself exist in quantum superposition, with every possible observer simultaneously creating every possible universe? The observer effect might also function in reverse. Just as our observations may be creating the reality beyond our horizon, observers in other regions of the multiverse might be creating our reality through their observations. We might be the product of alien consciousness collapsing quantum wave functions in their observable universe. This creates a cosmic feedback loop where observers create reality and reality creates observers, rendering the boundary between mind and matter fundamentally meaningless. The edge of our universe might not be a location at all, but a process of ongoing creation driven by the mysterious interaction between consciousness and quantum possibility. But what if consciousness, rather than a mere observer of reality, is the very foundation from which all existence springs? What if consciousness did not emerge from matter, but is the fundamental fabric from which matter, space, and time themselves are woven? This revolutionary concept, known as panpsychism, proposes that awareness is an intrinsic property of reality, akin to mass or electric charge. Every particle, every atom, every quantum field might possess some rudimentary form of experience. The intricate consciousness you currently feel would then be a composite of countless minuscule conscious moments occurring throughout your brain and body. Envision consciousness as a spectrum, not a simple on-off switch. At one extreme lies the rich, complex awareness of humankind, with its thoughts, emotions, and memories. At the other, perhaps the minimal awareness of an electron responding to electromagnetic fields. Between these extremes lies a full gradation of consciousness, from the collective awareness of ant colonies to the potentially alien consciousness of entire ecosystems. If consciousness is fundamental, The boundary of our observable universe might not represent a limit of space or matter, but a limit of the cosmic mind encompassing all existence. Beyond our horizon could lie regions of reality where consciousness operates under entirely different principles, manifesting as forms of awareness we cannot presently conceive. Some panpsychism theories posit that the universe itself is a single, vast, conscious entity, experiencing reality from countless perspectives simultaneously. Every human mind, every animal brain, every conceivable form of awareness would function as neurons within a cosmic brain spanning all of space and time. Our individual consciousness would then be transient patterns within this universal mind, analogous to waves on an infinite ocean. The mathematical framework of quantum mechanics might actually describe the behavior of this cosmic consciousness, rather than unconscious matter. What we term wave function collapse might be moments when the universal mind makes decisions regarding reality's unfolding. The uncertainty principle might reflect the inherent creativity and spontaneity of consciousness at its most fundamental level. If consciousness permeates all of reality, then the regions beyond our cosmic horizon might harbor forms of awareness, operating on scales beyond our comprehension. Galactic consciousness spanning millions of stars, dimensional consciousness existing across multiple universes, temporal consciousness experiencing past, present, and future as a single, eternal moment. These cosmic minds might surpass human awareness as much as human consciousness surpasses the simple responsiveness of bacteria. Their thoughts and experiences might unfold over millions of years, pursuing goals and purposes encompassing the evolution of entire cosmic structures. The discovery of consciousness as a fundamental principle would revolutionize our understanding of what lies beyond the observable universe. Instead of questioning the existence of additional matter and energy, we would need to inquire about the types of awareness present in those distant realms and how they perceive reality. But perhaps the most profound implication is that your consciousness, the awareness currently reading these words, is not separate from the universe, but the universe experiencing itself subjectively through your unique perspective? The ultimate question arises: what does it mean to be a conscious being within a conscious cosmos? How does individual awareness relate to the encompassing infinite mind of all existence? Consider this. What if our universe originated by information traveling backward through time, causing its own inception? This is the cosmic parallel of the bootstrap paradox, a logical enigma where an effect becomes its own cause, resulting in a closed causal loop with no true beginning or end. In cosmology, this paradox offers a potential explanation for our universe's existence without needing an external creator. For example, imagine a time traveler providing Shakespeare with a copy of Hamlet, which Shakespeare then publishes. Years later, the time traveler retrieves the play and repeats the action. Where did Hamlet originate? The information appears to exist without creation. Our universe might function similarly. Quantum mechanics permits information to propagate backward through time under specific conditions. If our universe develops sufficient complexity and consciousness to eventually achieve time travel or backward causation, information from our distant future might be responsible for meticulously adjusting the initial conditions that enabled our very existence. Envision this cosmic feedback loop. Billions of years in the future, advanced civilizations discover how to transmit information backward through the quantum foam of space-time. They utilize this ability to modify the fundamental constants and initial conditions of the Big Bang, ensuring the universe's evolution precisely produces those same civilizations. The universe becomes its own architect, engineering its existence via temporal loops spanning cosmic history. This bootstrap mechanism could explain the remarkable fine-tuning observed in physical constants. Why is gravity's strength precisely what it is, allowing star formation? Why do nuclear forces possess the exact properties necessary for the existence of heavy elements? Instead of requiring external design or selection from an infinite multiverse, these values might be a consequence of our universe's future, influencing its past. The regions beyond our cosmic horizon might be the origin and termination points of these temporal loops. Information traveling backward through time might emerge from future universe states existing outside our current observable boundary. The edge of our cosmos might not be a spatial boundary, but a temporal one, where cause and effect relationships become circular and self-sustaining. However, the bootstrap paradox presents profound philosophical questions regarding existence and causation. If the universe creates itself, what provides the initial information or energy to initiate the process? How can something be its own cause without prior existence to enable the causal loop? Some physicists propose that the bootstrap universe exists in a state of necessary existence, where self-creating loops are so logically interconnected that reality has no other option but to exist in this precise configuration. The universe would resemble a self-proving mathematical theorem, a self-evident truth that cannot be otherwise. If our cosmos is indeed a bootstrap universe, the search for what lies beyond our horizon becomes a quest to understand the mechanisms of cosmic self-creation. Yet, perhaps the deepest enigma is not how the universe creates itself, but what makes existence possible at all. Everything you perceive as real, matter, energy, space, and time, might be merely patterns of information processing within a cosmic computational system. This radical concept, known as digital physics, posits that the universe's fundamental building blocks are information, not physical substances. Each particle, force, and quantum field would then be a data pattern processed by the ultimate computer, reality itself. The edge of our observable universe may not be a spatial boundary, but rather a limit to computational processing capacity. Consider how a computer simulation generates the illusion of complex worlds, using only ones and zeros. Digital physics proposes our universe operates similarly, but instead of binary code, it utilizes quantum information as its fundamental currency. Every interaction between particles would constitute a computation. Every physical law would be an algorithm, and every moment of time would be a processing cycle. The evidence supporting this information-based reality is surprisingly compelling. Quantum mechanics already describes the world in terms of information, not classical properties. Particles lack definite positions or velocities until measured. They possess only probabilistic information. The laws of physics can be reformulated as statements about information processing and computational complexity. Black holes offer the strongest evidence for reality's computational nature. The information capacity of a black hole is proportional to its event horizon's area, not its volume. This suggests space itself might be emergent from more fundamental information processing. What we experience as three-dimensional volume could be a holographic projection from two-dimensional information storage. If the universe is computational, then regions beyond our cosmic horizon might represent areas where different computational processes are active. Some regions might be executing programs for universes with different physical laws. Others might be running simulations of potential future histories. Still others might be processing pure mathematics, exploring every conceivable logical structure. The computational universe hypothesis also explains the mathematical nature of physical laws. Mathematics is not merely a descriptive tool. It is the programming language in which reality is written. Every equation in physics would be a line of code in the cosmic program. Every symmetry would represent an algorithmic optimization, and every conservation law would be a constraint within the computational system. However, this raises profound questions about the hardware executing this universal computation. What is the physical substrate that processes all this cosmic information? Some theories propose that space and time themselves emerge from pure information processing, requiring no underlying physical hardware. Reality would be software without hardware, information without a storage medium. The computational nature of reality might also explain consciousness. Your thoughts and experiences might be subroutines within the universal program, temporary information, processing patterns, creating the illusion of separate existence while actually being part of the larger cosmic computation. If reality is information, then the ultimate question regarding what lies beyond our universe becomes: what is the source code of existence itself, and what transpires when we encounter the boundaries of the cosmic program? At the edge of human understanding lies the ultimate prize, a single equation explaining everything, from quantum particles to cosmic horizons, revealing what transcends the boundaries of space and time. This theory of everything would unify quantum mechanics with general relativity, clarifying how gravity functions at the smallest scales, and how space and time arise from more fundamental structures. It would unveil whether our universe is unique or merely one pattern in an infinite tapestry of mathematical possibilities. The pursuit of this ultimate theory has propelled physics for over 100 years. Einstein dedicated his final decades to seeking a unified field theory, describing all forces as manifestations of curved space-time. Currently, string theorists posit that reality comprises tiny vibrating strings within 11-dimensional space. Loop quantum gravity proposes that space itself is composed of discrete units smaller than atoms. But the theory of everything might reveal something far stranger than any present-day hypothesis. The mathematics could demonstrate that reality possesses no fundamental level whatsoever, with each apparent foundation dissolving into patterns of something even more basic. We might discover that existence is an infinite hierarchy of emergent properties, where each level of reality is constructed from the level beneath, lacking any ultimate grounding. Envision reality as an endless series of Russian dolls. Opening each doll reveals another within. Atoms are made of particles. Particles are made of quantum fields. Quantum fields might be made of strings. Strings might be made of something else. And that something else might be made of something even more fundamental. The theory of everything could reveal that this descent is unending. Alternatively, the ultimate theory might show that reality is circular rather than hierarchical. The largest structures in the universe might be built from the smallest ones, and the smallest ones might be built from the largest ones, creating a closed loop of causation without beginning or end. The edge of our universe might connect back to its center through dimensions beyond our perception. The theory of everything would also resolve the enigma of consciousness by demonstrating how awareness emerges from, or relates to, the fundamental structure of reality. It might reveal that consciousness is a fundamental aspect of existence, or it might show how complex information processing naturally leads to subjective experience. Most importantly, the ultimate theory would tell us what exists beyond our cosmic horizon by explaining the true nature of space, time, and existence itself. It might show that our observable universe is one cell in an infinite organism, one note in an eternal symphony, or one thought in a cosmic mind encompassing all possibilities. but a haunting possibility drives many physicists forward despite the immense challenges. What if the theory of everything is fundamentally incomprehensible to human minds? What if reality is so alien and complex that no finite intelligence can ever fully grasp its true nature? The search for ultimate truth might reveal not answers, but the beautiful and terrifying limits of human knowledge itself. Yet, perhaps the most profound discovery would be what this search reveals about the meaning of being conscious beings in a universe that may be far stranger than we can imagine. The answer to what lies beyond our universe will transform not just cosmology, but the very meaning of being human in an existence that might be infinite, computational, or unimaginably alien. Should our universe prove to be merely one bubble within an infinite multiverse, the implications for human existence would be simultaneously awe-inspiring and humbling. Precious, because within that infinite expanse, the precise arrangement of atoms and experiences that constitutes your unique self becomes extraordinarily rare and special. Humble, because the sheer scale of existence would dwarf our civilization to insignificance, akin to a single grain of sand upon an endless beach. The discovery of parallel universes would necessitate a profound reassessment of identity and choice. If countless versions of you exist, each making every conceivable decision, what then imbues your specific choices with meaning? Does the concept of free will retain its potency if every potential outcome is realized somewhere within the multiverse? These are not merely philosophical quandaries. They are practical questions that would reshape our ethical frameworks, legal systems, and personal sense of responsibility. A computationally based reality would revolutionize technology and human potential. Understanding the universe as an information processing system might permit direct interaction with this cosmic computation, potentially granting us godlike abilities to alter physical laws, manipulate space-time, or even upload consciousness into the universal program. The revelation that consciousness is fundamental rather than emergent would transform medicine, psychology, and our comprehension of mortality. If awareness pervades all matter, then techniques to enhance, transfer, or preserve consciousness could become feasible. Death might not represent the cessation of existence, but rather a transition to different forms of cosmic awareness. Perhaps most significantly, understanding what lies beyond our cosmic horizon would resolve the question of cosmic loneliness. Are we alone in a void, or part of a vast community of conscious beings dispersed across infinite realities? The answer would dictate whether humanity's ultimate destiny is solitary expansion into the emptiness of space or integration into a cosmic civilization beyond our current capacity to imagine. Yet, the very pursuit of this knowledge might surpass the importance of any answer we uncover. The human drive to explore, to question, to transcend every boundary is uniquely human. Even if we never definitively resolve the mysteries beyond the universe, the journey itself transforms us with each step. Every telescope we construct, every equation we solve, every boundary we breach elevates us beyond our previous limitations. The cosmos has given rise to beings capable of contemplating their own cosmic insignificance. And that capacity for wonder might be the most remarkable development in the universe's history. If consciousness truly is rare and precious within the cosmos, then humanity bears an immense responsibility. We might be among the few species capable of understanding and preserving the knowledge of reality's true nature. Our survival and flourishing might be necessary for the universe to attain self-awareness on a cosmic scale. The question of what lies beyond our universe is ultimately a question of